cable operators, SIP providers, things like this. We do a bunch of software associated with this business of having multimedia service platforms. You might know some of them. We do Blink, which is a SIP client, SIP server, or SIP application server / conferencing server / WebRTC gateway / we put many of things there. Media proxy for your net traversal needs, you know as well, CDR tool, CDR mediation tool, and some others like OpenXCAP, Control, and so all around these things we need beyond the SIP proxy to operate these kinds of platforms. One such platform we operate, other than selling to our customers, is Sip2Sip. This is a free service hosted at Sip2Sip.info. Do any of you know it exists and stuff? Okay, a few of you do. Well, for us, it's a test bed. So we have we went all in with all the features that we can implement. So, of course, audio, video, we don't touch the RTP other than for net universal, so that's fine. Then we support chat using MSRP, presence, using the whole SIP simple maze of standards, XCAP, and we try to implement, or we try to show what SIP beyond VoIP means to us. This is kind of what we've been doing since the beginning, and we try to showcase it. So setting up this infrastructure, even if it's not scalable whatsoever, even if there's one server of each, you need a lot of equipment, a lot of configuration, okay, not a lot of equipment, but a lot of moving parts, like where you need your SIP proxy, OpenXCAP, your net traversal, these, that, and everyone like working together. So if you want to check out how these services work together, this is a quick and easy way to see. Then for us it also helps because we've seen all sorts of crazy, broken, stupid devices connect to our network, which means we learn from it, and once we fix it, and all our customers get our fixes, we use a consistent configuration so everyone gets the same thing, and once we fix it somewhere, it's just fixed. This is a free service, so any one of you can create an account there and just test it out, see if you like it or you want to see how it works, you'll see traces and stuff. You can just go in and use it. And it has been growing around the years, like steadily a little bit, as in it's not super heavily used because, as I said, it's like a testing platform for us and everyone can put whatever they want there. However, not many people want to run their business off this kind of thing, right? For us, it's testing. But there is roughly 3,000 SIP accounts active at any given time. So we use this to experiment with the system we have built over the years, see how it behaves, scale it up, scale it down, test it out. And this is sort of where I want to get into today, into the innards of the way we do scalability, which I wish my talk was yesterday, because you would remember that in 3 of the talks yesterday, scalability was mentioned in all sorts of different flavors. And then I'm going to review them quickly, and then I'm going to show you the one we do. So in scalability, there are many ways to do it, and it's all about getting the high numbers, I guess, in the chart. So you have more requests per second than anyone. And there are many ways to do this. The typical way was to use a master-slave sort of couple of proxies for resiliency, as in you want to scale in this is more for resiliency than anything, as in, oh, if my big SIP proxy dies, at least I have another one. But this, as he said yesterday, involves like a double default. You need 2 of everything, and half of your equipment is just collecting dust. And then the day you want to actually take over, your server is not working because nobody checked. I mean, the intern put a Bitcoin miner and nobody knows what the server is doing anymore because nobody cared. So then, like, we got our people to procure some load balancers, and we built this interesting infrastructure with our big ass load balancer and some more load balancers and then few proxies, and looks like we're in business. But then, like, our load balancer can't balance the load, so we just call Oracle and like get a bigger one. and at some point your load balancer can't handle the load, you buy a bigger one. You kind of guess where I'm going, right? You get bigger one. But then who load balances the load balancer? Nobody knows. So here is where we try to use a different approach to achieve scalability. But in my personal opinion, scalability is not only about the technical aspect. So first and foremost, yes, scalability is requests per second, but we want that to go up, but I want my tickets per day to go down. Like, I don't want to deal with issues. I want a system that I don't have to mind and be checking every day. I want to go out and eat steak and not worry about my systems going down. Our company, it's 4 people and 2 of us are here, and we're not worried because hopefully nothing is breaking today. So the idea is that you also want to scale for your humans in your company. You don't want to be worried all the time that something is going to fall down. So we want our resiliency, our fault tolerance to go up. We want to engineer for failure because it will happen. It doesn't matter how expensive your power supply is, or your double internet and your triple power companies. There will come an excavator, will dig a trench next to the data center, and will just put everything in the dark, and the diesel generator didn't do the maintenance, and the whole thing goes on. It can happen, and it will happen eventually. So engineer for failure. Failure will happen, so we just deal with it. And we want to completely, or as possible, reduce the maintenance and, of course, the downtime. So we want a system that works kind of on its own. We don't want to take care of it. And this system we built is called Sip2Sip. This was first deployed in 2006, 2007. And let's go with buzzword bingo. It's a distributed, horizontally scalable, self-organizing, peer-to-peer network overlay. And what does that mean? Well, it's distributed because there are multiple servers working together to give you one piece of functionality, different pieces of functionality, but groups of servers given pieces of functionality. It's horizontally scalable because we can just put more servers into the network and they will get a chunk of the load automatically. And suddenly we can we say, oh, we need more servers. Okay, we provision either a VM with some orchestration tool, or we go to the data center with the rack, and we put it in there, we put some TLS certificates, and boom. 1 minute later, our server gets low and it's distributed. It's self-organizing because the network monitors itself. We said we have a bunch of servers giving this idea of one big server and distributing the load, but what if one of them, like, is bad. And it's a peer-to-peer network overlay. This is the technology we use. Is based on kind of core, kind of Kademlia, kind of not really, but it's based on this idea of distributed hash table lookup, which is ultimately, this is the last thing that Laszlo had in his talk. Like, we're looking into doing the core thing, and it's like, great, because tomorrow I'm talking about that. So this is how it looks, let's say. So in this diagram here, we have like a virtual ring, and this virtual ring it represents one service or many services. So each service in your infrastructure is represented by a bunch of servers that look like one. Say your seed proxies, your voicemail servers, your media relays. They are all kind of like this, virtually. So there's a bunch of them working together to make the thing run. And when you have a bunch of devices connected to each other, your signal then will go through one proxy or more, we'll see soon. And your RTP media will go through a different one. And this illustrates that, for example, here node 4 is a SIP node, so it's handling SIP traffic. It could also handle RTP if we also make it a media relaying node. But in this case, it's node 3, for example, the one that is handling the media. Now, at the core of this is the built-in internet load balancing protocol that everyone knows, but not everyone realizes. And it's DNS. And that's what we use so that you join the ring. You can find that the ring is composed of all these nodes. So let's see how it looks like. And you can actually do this in your terminal because this is publicly available. So if you do an actor lookup for the Sip2Sip.info domain, remembering the SIP lookup mechanism, there you will get the priorities of the SIP transports you want to use. So our first priority is to use TLS, then TCP, then UDP. Now if you look at this, there's nothing here that is dynamic, as in you're not changing these records every day, right? You're not switching transports arbitrarily because you don't need to. So these records can be statically provisioned, and they are there, they change very rarely, and that's fine. Now let's continue our lookup mechanism. We do the SRV lookup for the TLS record, and it tells us that this is in port 443 in a proxy SIP port net. Still, nothing truly dynamic because this is a hostname and that's a port. I don't think you change the port where your proxies listen every so often. So this is also some data that doesn't change. So then where is my servers? My servers are in proxy SIP port net. So in this zone we need to handle. So we need to be in charge of putting records on this zone. This is what is going to change. So as we see, there's the TTL is not big. I think we have like a minute or something. The idea being, when you do a lookup, you'll get 3 nodes here, and you'll try to connect to one. This list is randomized to like shuffled because some SIP clients are stupid and they'll just take the first record and go on with their lives. So next time you do a lookup, you'll get a different ordering. But if a node goes down, if this server breaks, the IP address will vanish from DNS. And because of the low TTL, the next time you do a query, you will not get it. And even if you get it, because we are still detecting if the node is down or not, you'll fail to connect and you will use any of the other records in the thing because you never get one IP here. I mean, unless you have torn down your whole platform, because the whole thing is to have multiple IPs here, because of course what you want is your distributed system. So you need to be able to connect to these multiple nodes. And now how does this happen? Because it's very nice, Saúl, I like your ring, but how do I join the ring? I have a computer here, and what happens? Well, this server of yours, you want it to become a node in your ring. Let's say, since we're here, that is a SIP proxy, and we want it to take SIP load. So we will give it a TLS certificate, and we'll just boot it up and configure it just with, let's say, the SIP proxy template, because they're all the same. And you will look in the DNS where the network overlay is, connect, and if his TLS certificate is valid, and let's say he's allowed in the network, then we have these bad boys here. And these are the DNS managers. And they'll say, oh, looks like a new node joined the network. Let me add it to DNS. I know how to do that. So they modify, in this case we use Power DNS, and we can modify the database just fine. We add a new record, and then you do a new lookup, and boom, you have a new A record in your table. So that's how we distribute the load. Basically, you can imagine that every SIP client that is doing DNS lookups and DNS lookups and sending your packets, it will arrive based on this scheme, and because we shuffle the list, evenly distributed to any of the IP addresses we saw before, right? Now, you're now probably wondering, that's a cool story, but if you have 3 nodes and my invites can go to any node, is like the user, the subscriber's information, is it in every node? Or how do we achieve partitioning? Because the way to scale this whole thing up, and I don't mean 3 servers, imagine 3,000 servers, is by not replicating any data. That means that each node should only have the data that pertains to their own users. That is, Okay, if we have, let's say three, so we have three servers with 1,000 accounts each, or let's say 3,000 accounts and three servers. Each server should only have information about roughly 1,000 accounts. Because if you multiply this by 2 orders of magnitude, you're not going to have all the profiles accessible to all of them. And how are you going to replicate the data across your 3,000 servers? Yeah, not happening, right? So, way we do this is by leaning in the nature of the peer-to-peer network overlay, which is a distributed hash table lookup. And in a nutshell, what this is, or the way this operates, is we got this SIP account, which is my SIP account, and we apply a distributed hash table lookup. And we look it up for a resource, because as I said, those rings, those virtual rings we build, they are for different things. We have SIP proxies, we have media relays, we have voicemail servers. So what is the node? What is Saúl's node for this resource? And that tells you node X. Node X is one of the nodes in the ring. And this is important. This defines what we call a home node. And your home node is the proxy that has your data. All the other proxies don't have your data, but one of them does. And this function is the one, the function that allows us to know where to go. Now, it's critical that this function is A, fast, of course, and B, that you don't have to go anywhere to do your lookup. In pure cores, you are not allowed, you're not able to do the lookup yourself unless it's to both of your neighbors. But so you ask around your peer-to-peer network and you find it. But think about it this way. In the typical peer-to-peer scenarios that we know, like Kademlia, BitTorrent, these kinds of networks, we have hundreds of thousands of nodes. So it's impractical to kind of keep a routing table to go to each and every one of these nodes and keep it up to date. But here we're talking servers. We're talking at most thousands. So this is very cheap to keep. So this function, every node knows this function. And it can apply it because it knows how the network is at any point in time. Each node knows that there are other 5 nodes. So when you apply this function, you can say, okay, Saúl modulo 5 nodes, 3rd node. This is like the kind of back of a napkin way of saying what this does. But another property very important from this function is the H is for hash, but not any hashing function will do, because if you have our previous scenario, 3,000 accounts, 3 servers, if one of them dies, now we have 3,000 accounts, 2 servers. But we don't want the whole thing to shuffle and all the accounts to have to be moved from one server to another by some dark magic. Ideally, we would want the 1,000 accounts that belonged to that node which died to be kind of 500 here, 500 there. And the hash functions that kind of have this property are called consistent hashing functions. And these allow for a hash table resizing without having to move the data left and right and not knowing what to do with it. So let me show you what the more kind of complicated, let's say, lookup looks like. So let's say Alice wants to call Bob, like per usual. So you do a DNS lookup, and you end up with those X number of addresses. And you send the invite to the first node that you find, because that's what you do. So you send it here to node 2, and node 2 has a visual of the network, as does every node, and says, where is your home node? Where is Alice's home node? Well, it says it's node 3. All right, so it sends the invite here. Now let's assume that node 3 is, let's say, cold, as in we just booted it up. Node 3 looks at his database and says, yeah, I should have your account, but I don't. So what happens here is, as you can see, these black boxes here are databases. So each node has a a local database which is disposable. So when we shut down the node, the database doesn't matter. One thing note in this picture, because it's hard to make all the connections, is when a profile is required here, it's copied. It's just there, and then from now on, we just update it. Every time you change, and by user profile, I mean username, password, all the call forwarding rules, whatever we need for this routing thing, we copy it to the database, to the local database, and whenever it changes, we update it. So there's no more need to copy. There's no need to replicate the data everywhere. The central database will stay pretty idle, and while ideally, as I will mention in a little bit, you would want to have like a super highly distributed storage, in practice you will run into other limits before you actually need to do that, because of the fact that each node only handles one piece of the cake, and the central database doesn't have load, because the load is on the individual database that each node has. And if you dimension for this, let's say you have your infrastructure is an open stack architecture, and you say, well, okay, I have battle tested this, so a couple of cores and 8 gigs of RAM, 15,000 subscribers. So you just take this template and multiply by the number of people you want, and you boot them up. So they can be called. They will fetch the accounts one by one as they are needed. And one of the tricks here is if I don't have your data, but I should, I won't reply to your invite, and then you will retransmit it, and by the time it comes, I will have it, and I will be able to authenticate it. Otherwise, I will have to fail the first time. It's bad user experience, but the next time I will have it. And the hash lookup function, I think we benchmarked it at around 400,000 lookups per second. So that's not going to be like your problem. So back to where we started. This node now has your profile, so it can authenticate you. So the invite is accepted. Let's move forward. Who is the invite for? Bob. Okay. Bob must have a home node too. Like, where is Bob? Okay, we do a lookup for Bob, and we get that it's a node 4. Okay, so we send the invite to node 4, and here we do we do a lookup in our location table, because we know we're responsible for Bob, right? So he must be here. However, we find that Bob is not here. As in, yeah, I'm responsible for Bob, but, and here we use a similar thing to path. Are you familiar with path? Sip2Sip. Yeah, that, okay. So what happens is that because we do this DNS lookup, you may end up sending your register to a node that is not yours, and then it needs to be forwarded to the node that knows how to authenticate you. Let's say that Bob registered, well, actually, let's say we know that Bob registered through node 6. Now, what happened was that node 6 is actually doing NAT traversal for this user. And then after doing the NAT traversal treatment, it followed the register to his home node, and then it was authenticated and saved into the database. And this is equivalent to what SIP path gives you, which is you basically put an outbound and inbound proxy in the path. So when node 4 does lookup location, you get, yeah, you need to send it to node 6 first. So you send it to node 6, and node 6 is, oh, okay, I'm the final relay, I'm the entry point, I'm the one directly connected with Bob, and I send the invite. And then invite happens. Now, the media, however, doesn't need to do all these dance, because your home proxy is the one that will do the NAT traversal for you, make it easy. So once the invite comes here, we fix it before we send it out, and then the media ends up just traversing one node. Now, this looks complex, and it's complex, but it's not complicated. At most, you will get 4 nodes, because if you think about what Alice and Bob did, each of them, let's cut this in half, they registered through one node, and then their home node is another one. But by chance, you could end up in arriving straight at your home node, or you could both be on the same home node. And having 4 hops in practice hasn't turned to be bad for us in our experience so far. many years. And the reason why we like this model and why similar things have been attempted but didn't succeed, which is peer-to-peer SIP, is this works with normal devices. Take any SIP client that is at least worth looking at, so it can do DNS requests. And it can participate here because for them, they don't have to know anything special about how the DNS is managed, the platform, how many SIP proxies are 2, 4, 7. Who cares? Nobody knows. They don't have to do any special lookup. Ideally, not ideally, but maybe you would want to say, well, okay, normal endpoints, they can do the typical DNS lookup, but since I am actually a device manufacturer, or in our case, we do a SIP client of ourselves, we could have baked in the lookup mechanism to try to optimize the path and remove 2 nodes. But in practice, we didn't even do it because there was no need. This just works. Your inter-data center connections have to be fast enough. And they will be. So, and if you run into like packet size limitations because of all the vias and record routes, you can always apply topology hiding here. Yeah. If need be, and then you make a very small packet on the way out, like nice and clean, and nobody knows how many nodes are behind or what's happening here. So this is the model we came up with, which is not absent any challenges. And I'm going to mention a few of them because, well, time is limited here, and I want to take questions if you have them. So. I could spend a week in all the details of the many pieces that compose the infrastructure, but I'll tell you what is hard to kind of achieve, let's say. One of the interesting things is the distributed storage. As I mentioned, right now we're running a central database with the user profiles that then gets, like, each node copies the data from here. This is one of the things that we would like to at some point improve. As in, okay, if we have all these machines, they might belong to a big distributed storage system, and then, well, we can just pick the data from this big storage system. Now, when we did this, so this started in 2004, 2005, the landscape was a lot different. But today, we have a lot of distributed databases around. It's just a matter of looking if one of them actually fulfills all the things you want, just the way you want, because many of these databases have things like eventual consistency, and, well, you might be more interested in right them now consistency, not maybe tomorrow. So you want, like, it's your passwords. So if you get the data wrong, well, it results in day one getting another 407, and then, well, the user has to redial, let's say. So ideally, you want to minimize that. Another point is accounting. So accounting is typically a centralized process in the sense that the bills need to go to one big place where they then get sent to people and stuff. So even if we have multiple nodes, at some point we need to collect all this information to make sense of the CDRs to be able to do the billing and send it to our users. And this is one of the things we want to find a way to scale up, let's say, when it comes to that. But then again, not all calls are accounted for equally. There are many systems. So this is one thing to look at. And one last thing, and I think I asked Razvan about it yesterday, is the registration expiring. There's an interesting thing that happens when you're here. When nodes go up and down, like, your users are unreachable at that point in time, right? But if we think about kind of the present, in the sense that you're not using UDP, right? You're using TLS. So if the TLS connection is broken, the client will notice and it will try to reconnect. But if the client connected to this node, and then this node connected to this node, and this is the node that keeps my that has the information about me, where I am, my registration. This could go down. And if this goes down, then basically we need a way to tell this guy, hey, this is not reachable right now, you need to reconnect, so we know. So one way to achieve this is, of course, with low registration intervals. So A, you want to find the sweet spot, and B, I think in practice we didn't have issues with this, but if you really want to optimize this further, an interesting thing would be to use a notifying mechanism between the entry point and the home node. So as you say, hey, well, actually not a notify mechanism, but like this, when this guy realizes that this guy has gone, it needs to like tear down these connections to force them to be recreated, because the endpoints will reconnect. But you need to tell them that they have to. So that's another challenge. And well, the last one, which is not here, is that one unfortunate occurrence is that I cannot give you the source code for Zipper. It's what our company has been doing for a long while, and unfortunately, and it's not my call, it's not open source. However, all the information is out there, as in, we never hit it. The only reason why I'm giving this talk here today is because every time we get to talk about another piece of software we do, someone asks, but how do you scale it up? And then they're like, yeah, we have a peer-to-peer network overlay, that this, and that. And then I always get the question, can you tell us about that? So, okay, here I am today telling you how it works. Feel free to ask any details on this, but source code is not available. So if you have a scaling problem, better call Saúl or better call us as well. And if you have any questions, I left some time, so hopefully we can discuss, because I also was talking with Rasman yesterday. OpenSIPS is working along these lines, and what I have seen so far, and actually only by judging the talks that we've seen so far, we have had something to do with scalability. You end up with master-slave, and you always end up wanting to record somehow. Yeah. Thanks.
Anybody have any questions?
Isn't the centralized database a single point of failure?
Well, if you look at the central database as one entity, it is. But in practice, it's not one node, it's a cluster of nodes. But it's true, conceptually, is a role which is the first thing you want to remove with a distributed storage. However, as I said, in practice, because it gets so little load, as in you typically, once your platform is stable, as in you're not going to be putting nodes up and down randomly like a madman. The things just run, you know, and you're prepared to handle the failure. And failure means, okay, like let's take catastrophic failure, which means a whole data center goes down. All those accounts are gone. So when those profiles are needed, they will be copied to the new home node, but one by one. So it's not like suddenly there is 30 gigabytes of data that need to be transferred in less than a second away. It's very small data. We use a JSON-based profile that goes over the network, arrives, and then we put it in the local OpenSIPS table, and then the invite gets it from there. So one thing I didn't mention is that all the pieces of software that actually make up the whole thing are unmodified. So we just have a tiny little, less than 500 lines, I think, a module for OpenSIPS that communicates via FIFO with someone who knows how to do a Tor lookup. So the whole thing is not dependent on that.
Anybody else?
Yeah. Yeah, go ahead. There was one there, I think.
Yeah. You said, talked about the challenge of the accounting.
Yeah.
Did you solve it, or is it still a challenge?
Well, it's a challenge in the sense that given enough load, if you have one place where you need to gather all your CDRs, you will need to figure out how to do it better. Now, where is the pain point? So far, we didn't run into it. We did look into possible solutions. Right now, we're using also MySQL as our accounting backend. We do accounting via Radius, which ends up in MySQL. But accounting is, so CDRs are not really that relational data. So one potential way to scale this up is to switch away to a kind of NoSQL-ish database that at least gives us the durability we need, that can handle these like more requests and more of these, can better handle the load for a non-relational data, which in a way CDRs are.
Do you have the accounting working on a node or separate?
Each node will send the radius information. The radius records are then gathered at some place, and then we run, these are all inserted, and what we do is we run an offline normalization process. So if a call gets, let's say, three radius records, like the start, update, and ended, for instance, well, in the update we get the media information. Then we make a single CDR out of them. So this process does not run in real time. It runs in batches unless one of the tools we developed, CDR tool, allows you to browse the CDRs online. So when on a website, so when you look at the website and you want to check one CDR, if it's not normalized, we normalize it on the spot. So this is also one way we have to not like have this massive load in working very hard on the CDRs.
Anybody else?
In the example, there was 7 nodes and it took 4 hops.
Yeah.
If there was, say, 20 or 30 nodes, could you potentially still always 4 hops?
Yeah, it's always 4 hops because, so what happens, I'll say again, be more clear, hopefully. This guy does a lookup, right? Comes up with any address in as many nodes as there are, it just sees one, whatever it is. Let's say this. And this node is the one that will keep his NAT open, okay? And then this node will forward it to his home node, which is this one. We have 2, right? Now, for the callee is the same, but on the opposite side. So it doesn't matter how big the circle is, at most you have 4.
1 or 4. In one, it's the same. I think they're both read the same, there's only one.
Yeah, it's possible that there's only one. I mean, if you end up connecting to your home node and your home node ends up being his home node.
It could be 1, 2, 3, or 4.
Yeah, it can be 1, 2, 3, or 4, but 4 is the absolute maximum based on this lookup mechanism.
Okay.
Related question, and may have missed the detail, is the home node defined in the profile of the user?
No. The home node is discovered dynamically using the distributed hash table lookup. What this function does, in a nutshell, is, let's say I have a list of all these nodes, right? Each node knows about the network because imagine that you're in this circle, right? Virtual circle, and they get messages go around this circle, like gossiping. Oh, I joined that node left. So each node knows about how the network is. So you have, let's say, a mathematical formula which says, based on the current state of the network and the input, which is your zip address, your home node is this. And if the network doesn't change, the result will always be the same. And if the network topology changes, as in a new node joins or a node leaves, then this could change. And in order to try to minimize that, we use a consistent hashing function, which will allow you basically to not move that many accounts. That's sort of the idea. As in, if you put a new node, initially no accounts are moved to him, because they're fine in their own nodes and stuff. But they will eventually gravitate until they are roughly evenly distributed. So this is a thing that is computed on the fly completely with the data that each node possesses. It doesn't need to go anywhere and ask for this.
So it just needs to know which other nodes are live.
Yeah.
And if you want to distribute your nodes geographically,
Yeah.
One in Amsterdam, a set in Amsterdam, a set in Tokyo, and a set in San Francisco. Is there any geographic overlay in terms of latency differentiation?
So if you want to do that, we're not concerned about that with regards to signaling. So sending the invite yada, yada, that's fine. Now, you might be worried about the media, because you want the media to be as close as possible. As in, if two users in Amsterdam are talking to each other, they will probably want to use a relay that is in Amsterdam. We did leave room for it, let's say, in the, I'm not sure if you're familiar with Media Proxy, our project. So Media Proxy right now, when you want to use a relay, it uses randomly across the relays that are around. And relays are resources, just like SIP proxies that join the ring. So we do have the place where we could alter this logic. And our approach would be a self-learning mechanism by which you know where, like, not necessarily geographically as in latitude, longitude, but what's closer in latency-wise. So what's the best relay, which doesn't necessarily have to be the one that is closest in proximity. So you would use an algorithm like this to realize who is closer to who, and then you will pick the best relay. But the signaling will go all across the SIP nodes. But then as well, there are other things you could do. For example, maybe you could put more than one actual server behind a single IP address with tricks like Anycast and like make kind of the overlays overlay. But we never had the need to dig that deep into the trenches because our customers so far have always been primarily focalized in one area of the world, not a global single big slab of things, but we did think that at some point someone will hire us to solve this, and when it happens, we'll solve it, or we'll try. More questions?
What's the HT? What is it?
What
function? Where does it come from?
It's the definition of peer-to-peer overlay.
I understand.
It defines what the hash function is. So it's a map.
What do you use for the? What do you use for the?
What do you?
What's the core of the hash? What do you use?
Well, it's the SHA-1 of the server plus extra information. But if you check the Wikipedia page for port, for example, you can see there how you actually compute the. But you can imagine it as follows. You convert, like the simplest possible way of thinking about it is convert that thing into a number modulo of number of nodes. And it gives you one number in the range of the nodes. But then this would be kind of sort of not very evenly distributed. That's why this thing is more complicated than turn it into a number, do the modulo. So there are lots, the devil is in all the details, but there has been a lot of research in recent years, different peer-to-peer technologies. So they use different DHT functions and different ways to find nodes. Like the way we do it is one, but you can get inspired by other ways of doing a similar thing.
Did you say that if the home node suddenly drops out of the system, that it would take some time perhaps for the devices registered on that home node to re-register?
Yeah, this is possible, yes, because they don't know that the node went away. If they are connected directly to the home node via TCP, for example, they do know immediately because the connections are closed, but it's possible that they don't. Now, there is one thing that we attempted, but we ended up not doing because it doesn't work, which is try to force devices to register at your home node, which is when you arrive at the edge proxy, I send a 302 to the register, and I tell you go there, but good luck with that.
What happens if the home node disappears completely, so it blows up, you have to replace it?
No problem. When you try to re-register, the formula will tell you that your node is something else. And then you send an invite there, and the node because the nodes do the lookup themselves, like, am I responsible for this SIP count? And if the answer is yes, they look in the local database. And when you do this process, is it myself? Yes. Then the thing in kind of background is, give me the profile. If that is the case, fill out the database because I need to authenticate this guy? The answer is no. It tells you which is the node, so you can forward the request there.
What happens if that node's gone? What happens if the node's gone completely out of the network?
You do the lookup and the node goes down. In that case, the request will fail, of course. If it happens right between you doing the lookup and you sending out the invite, this is no different than you trying to connect to a server that goes down. It doesn't have anything to do with the fact that we run an overlay. But if the node goes down, because the network, we know that the node went down, we realize that. And once we know that, the formula, when you apply it over the new data set of nodes, gives you a different result, and then the mechanism starts again. So your profile, it's copied from a central database to a node's local database, and now we have it, and we can continue.
So they know that the network knows that node's gone down, and then will redistribute that node's home users to the other ones.
Well, the network doesn't do anything actively. It's a passive action, because whenever someone asks who is responsible for this, the answer will be different. So profiles will be copied on demand, profiles will be deleted as well as like, oh, this node left. Let's say this node left. Oh, looks like I no longer need to handle this account, so I can delete them from the local database. So that's the part, that's kind of the part that is better defined as the self-organizing part. So this whole thing is not an active thing when node decides, okay, I need to, no, it's based on the dynamism of this system.
Okay, that's all the
outside.
time we have for questions. I'm sorry. Saul, make it boring next time, okay? Too many questions.